Okay guys, so today it's a little bit weird to break this up into lessons because everything is interlinked. So you're probably having mad deja vu by now, thinking, man, these lessons are pretty much all the same. Um, they do, cover the same stuff mostly, but there is something new in every lesson. Okay, so we're looking at mechanisms and catalysts. I know you've already seen catalysts, you've already seen in grade 11 how it affects your energy graphs, and you know what it is, and you know that it's something that will affect the rate of reaction as well. Adding a catalyst will increase the rate of reaction, but we're just going to look at how it affects the mechanism. Okay, now firstly, ma'am, what is a mechanism? Mechanisms are basically, it's the step-by-step way that a reaction takes place. It's how we understand a reaction. So it's basically the fact that when you have your product, your reactants, remember they don't immediately go to your products. Okay? In real life, this is not happening. It's what we write on our page, but that's not what's happening. Remember, we learned this last year. First off, our reactants have to break their current bonds. So whatever molecules we have in our reactants, we have to split that up into individual ions, and then those ions will react to form our products. Hoping we remember what those ions are called. We call them either the intermediates or the activated complex. Okay, so actually what happens is first we break existing bonds. Okay, and we are left with what's called the intermediates. Sorry, it should be either intermediates or the activated complex, same thing. Okay, which are basically just free ions. Where's my green quick? Oh, sherbet, sorry. There we go, you're alright, sorry about that. Okay, so these are basically our free ions. Okay, and in order to do that, in order to break the existing bonds, remember we need to put energy in. Okay, energy is absorbed by the system in order to break those bonds. And then with these free ions, we can then form our products by forming new bonds. Okay, and when these new bonds are formed, energy is released. Okay, now we are going to look at more in depth in this. I just want to quickly sketch this. So if this were a, what should we do? Oopsie. Okay, let's say this was, okay, let's do that one. Let's say this was a endothermic reaction. Okay, so we release more energy than we absorb, remember? Other way around? Less. Yes, this is correct. So we start with less energy than we end with. Okay, so let's say, let's say we were doing an endothermic reaction. Quick reminder, the activated complex, that's up here, right? So the energy that is absorbed in order to break the existing bonds, that's this here, okay? The energy absorbed to break the existing bonds. We get to our activated complex, and then energy is released to form new bonds. We learned this in grade 11. Okay, now what I actually want to draw your attention to is, let's see if we can remember, what do we call this? The energy difference from your reactants to your activated complex. Okay, that is your activation energy. And that is the energy that was absorbed. So this energy absorbed in order to form your free ions, your activated complex, this is actually your activation energy. Okay, and we will write definitions for all of this nonsense in a little while. Okay, so yeah, I'm actually going to pause you there, erase the board, and we'll look at the next important thing. So this is just an explanation of what the reaction mechanism actually is. Okay guys, now when we look at the way that catalysts and other factors affect the rate of reaction, we're going to link it to this thing called the Maxwell-Boltzmann curve. Okay, now what this is a graph showing the probability of a particle having a specific kinetic energy versus the kinetic energy of the particles. Okay, now this graph can be a little bit tricky. So firstly, the way that it's going to look is we're going to have a little hump at the beginning, and then it sort of peters out towards the end. Now, The best sort of analogy that I can make for this is, I'm sure you've all heard on American movies and that sort of thing, they talk about grading on a curve, or yeah, like the marks were bell curved. That's got to do with the fact that when you plot, this is why I asked on WhatsApp if you've done probability ogives. So when you plot the amount of something versus some kind of scale from 0 to whatever your maximum is, the odds of, so remember probability is like saying the odds of, if I close my eyes and pick one at random, what are the chances that it. So let's say we compare this to the people in the school. If I close my eyes and pick a random kid at random, and let's say we were looking at their marks, their average marks, so say 0 to 100% for their class average, their personal average. Do you agree with me that there are more people in the school that are sitting on like a 50% average than are sitting on 100% average? Okay, there are more people getting like 50s in the middle than there are who are getting very high marks. And there are also very few people who are sitting at 0. There's quite a few people who are like at 40, 30, not great, but there are very few people, if anyone, at 0. So this, ideally, is the kind of graph you should get, where the chances of picking somebody who's in the 50s is the highest, okay? That's got the highest probability, compared to picking someone whose class average is 0. That's so low down. There's like a 1% chance of picking someone who's got a class average of 100% or a class average of 0%. Keep saying class average, a personal average. Okay, so that's kind of what this graph represents as well. We're talking about if I were to close my eyes and pick a particle, a random particle in a substance, what is the probability that it has a certain kinetic energy? Okay, it's much more likely that it's got on the lower side kinetic energy. It's very unlikely that it's got 0 kinetic energy, and it's also very unlikely that it has a very high kinetic energy. Okay, so that's basically what this graph is telling us. You can just compare it to, if you pick a person at random, compare it to their marks. More likely that you'll have someone with roughly in the middle kind of marks. So roughly in the middle, closer to the lower end, kind of kinetic energy. Higher kinetic energy is very unlikely. Okay, now I know in grade 10 we tell you that, and it is true, temperature is a measure of the kinetic energy, but it's more than that. Temperature is a measure of the average kinetic energy of particles. So even if I've got a glass of water at 25 degrees Celsius, not every single particle is going to have the same kinetic energy. Okay, some particles will have a higher kinetic energy, some will have a lower. As indicated by this graph, we can see we've got kinetic energies ranging. Okay, this is in one substance. Now, we also have to now link this to the collision theory. So quick reminder, collision theory, we need a few things to happen in order for a reaction to take place, right? We need our particles to collide, okay? They need to collide with the correct orientation. And they also need to collide with enough kinetic energy. Okay, so what this means is, even if I've got this many particles, tons and tons of particles, only a certain number of those particles has enough kinetic energy. So let's say that the activation energy for my substance is 50 joules, okay, and let's say on my graph that's 50 joules, then that means only the particles in here have sufficient kinetic energy to react. So only that amount of particles has sufficient energy to react. Okay. Now on your notes, I'm not going to just rewrite what's on your notes, you can read it on your notes, but on your notes we look at two things. We look at the effect on your Boltzmann curve of changing temperature as well as of using a catalyst. Okay, so very important here. I'm not going to erase it and start over, I'm just going to make a new heading each time, so you can make little notes on your note. So now we're looking at the effect of temperature change. What is it? Effect of temperature change, yeah. Okay, so on your notes, we're looking at the effect of temperature change on your Boltzmann curve and then how that affects your collision theory. Okay, when we change the temperature, what we're doing is we are increasing the kinetic energy of all of your particles. It might not be increasing it enough to pass that point, right? This is our minimum. It's got to get past this vertical line. But it's increasing some of them. It's increasing all of them, but it's increasing some of them so that they're now over the line. So what's going to happen if we increase the temperature is, the best way for me to imagine this is like a blob of like jelly. If you push it on one side, then the whole thing sort of kind of like blobs over a little bit. So we're going to have the same kind of shape, but it's going to have blobbed over, if you understand what I mean. So it's going to have sort of the same area under the graph. It's just going to have shifted a little bit. So squished down on this side and then moved over to the right on this side. So here you can see that the number of particles that have enough kinetic energy is now increased. We've got all of these as well. So increasing the temperature has increased, it's kept the kinetic energy required the same, hey? The minimum energy required to start this reaction is still sat at the same number. They still need this kinetic energy. All we've done is we've increased the number of particles that have enough kinetic energy. Okay, so increasing the temperature, the effect of temperature change, what it does is it increases the number, this is on your notes, I'm just highlighting it, it's very important. It increases the number of particles with enough kinetic energy to react. Okay, so remember, in order for a reaction to take place, particles must collide with the correct orientation and with enough kinetic energy. So now if I increase the temperature, it means I have more particles with enough kinetic energy, which means some of these collisions that were colliding with the correct orientation didn't have enough kinetic energy initially. Now they do have enough kinetic energy. Not all of them, but more of them. Okay, so that's why changing the temperature increases the rate of reaction. Okay, now the next one we're going to look at, where is my razor? I keep losing it. The next one we're going to look at is the effect of a catalyst. Okay, so this is all on your notes. Okay, I'm going to have to put the red back in. Okay, so we're done with temperature. Now we're going to look at the effect of a catalyst. Danielle, you'll be so proud of me. I now know when to use effect and when to use affect. I'm confident. Okay, so when we make use of a catalyst, I'm not going to write down the definition of a catalyst. You should know it's a substance that increases the rate of chemical reaction without itself undergoing a permanent change. Just also something I have written in the blockie on your notes, they will sometimes call it a positive catalyst. It's the same thing, okay? A catalyst or a positive catalyst, exactly the same thing. So if they ask you to define a positive catalyst, don't panic. Same thing as a catalyst. Okay, so its function, we do know this. We saw this when we did energy graphs. So let's just quickly draw an energy graph. A little sketch of one. Okay, so if we had an energy graph like that, then we know, I'm hoping we remember this from last year, that introducing a catalyst, all it does is it lowers the activation energy. Okay, so we're going to have our graph looking almost the same. The only difference is it's going to be a little bit lower at the top. Okay, let me actually exaggerate that a bit more. That's way too similar. Okay, there we go. So it's going to be lower at the top, so it's decreased the activation energy. Okay, we do know this from last year. Okay, it's decreased the activation energy when we used a catalyst. Okay, so what does that mean for this? When we increased the temperature, our blob moved, right? We had a scenario where more particles had the correct kinetic energy. What happens when you use a catalyst is you're not actually changing the energy of the particles. So you're not, what's the best way to do this? Okay, changing the temperature would be like getting everybody a private tutor, okay? Then everybody's average would move up. But using a catalyst is like lowering the pass grade, okay? It's lowering, now you no longer need 30%, my goodness, to pass, you only need 20% to pass. So we've lowered what is enough, we've lowered the bar, we've lowered enough, and as soon as you do that, it means more people now pass, right? So if, in this case, using a catalyst decreases the activation energy, it means this dotted line is now no longer the cutoff, okay? We're decreasing it, we're lowering the bar. So that means all of the particles that previously between here and here weren't good enough, these are now good enough. So we've lowered the bar so that these now also have enough energy. Okay, so what adding a catalyst does is it actually shifts the required kinetic energy to the left. It lowers the activation energy, which means more particles have enough energy. So temperature and catalyst both result in more particles having enough energy, they just do it in a different way. Temperature makes everything have more energy. Catalyst lowers the bar. It lowers how much energy is required. Okay, so effects of a catalyst. This lowers the activation energy. Okay, and in doing so, more particles have enough energy. Okay. Which means once more we're going to have more successful collisions if we look at collision theory. Everything links back to collision theory in this section. Okay, I just want to make sure there's nothing I've left out. Okay, so in your notes, I've included there a whole lot of definitions, explanations of how catalyst works, all of that, which is important. Okay, so basically we've covered everything. We've covered everything required. Everything that's in your notes that I haven't written on the board is still important. I've just highlighted the most important things and, in my opinion, the sort of trickier things. So for me, the trickiest thing to remember is the difference in how temperature and a catalyst affect the rate of reaction. Okay, they both increase the rate of reaction. They both do so. They both do so by increasing the number of particles with enough energy. But the difference is how that happens. So with temperature, you're physically increasing the number of particles with enough energy. With a catalyst, you're just lowering the bar. Okay, you're saying this was enough, it's too much, I'm going to say this is now enough, which means now I've got a whole lot more particles which do have enough energy. Okay guys, I'm hoping that's enough, and that is also the end of rates of reaction. So I'm going to leave you off there. Apparently next week you're getting it off. I don't know if at this stage, by the time you get this video, if you're going to have gotten that email yet, but it looks like you're going to have next week as a little holiday / catch up week. So we will, I guess when we get back to school, the first thing we're going to be doing is doing revision of rates of reaction, because I had a worksheet for you guys that you're supposed to be doing next week, but I guess you're going to do it on the 1st of June when you come back. Okay, I'll see you guys then. I miss your faces.